Hi current and prospective MASH users. My name is Melissa Pergandy and I am a postdoctoral associate in the Ying-Ga Research Group at the University of Wisconsin-Madison. In the following video tutorial, I will be introducing you to MASH Native's Discovery Mode workflow. It is important to note that this video tutorial is intended to be used in parallel with the step-by-step instructions found in the Getting Started guide, which can be found in the Documents folder in your MASH Native download package. MASH Native has the capability for analyzing both native and denatured mass spectrometry data and includes spectral deconvolution and database search tools. The Discovery Mode workflow is intended for analysis of an unknown protein or proteins. In this video tutorial, we will walk through Tutorial 1, Analysis of Mass Spectrometry Data Collected under Native Conditions for Identification of an Unknown Protein. Please pause this video and download the Native Discovery Mode tutorial folder to your computer and save it to a new local folder if you have not done so already. Alright, let's begin. The goal of this tutorial is to identify an unknown protein from a bovine extract analyzed by mass spectrometry under native conditions. To do this, we will first walk through the deconvolution and assignment of charge states observed in the MS1 spectra. After this, we will walk through the deconvolution and database searching of tandem mass spectrometry data for the identification of the unknown protein by fragment matching in MASH Native. Shown here is the main MASH Native interface. To start, click on Import Data in the Discovery Mode node. Use the Import Data function in this node to import the sample bruker.d native MS1 folder. To do this, first select the bruker.d data directory. Next, select the native ms1.d folder from the local directory where you have placed the downloaded tutorial folder. Next, click OK. To deconvolute this spectra, we will use the quick deconvolution function, which has been configured to use the eThrash algorithm. For details on configuring this quick deconvolution function, please see the step-by-step instructions in the Getting Started guide. Here, select the Decon button to deconvolute the native MS1 spectrum. Once we do this, this will open the Workflow Manager window. You can use the Workflow Manager window to check on the status of your run. When your run is complete, the queued workflow box will be empty. You will then see the workflow in the Completed Workflows tab of the Workflow Manager. This indicates that the analysis is finished. You can now close the Workflow Manager window by clicking on the X in the upper right corner. In the main MASH Native interface, you will now see that the mass list is populated. Here, users can manually review the deconvolution and isotopic fit in the Results View panel by clicking on each line. To adjust the isotopic fit, use the arrows found on the top of the MASH Native interface. To alter the theoretical fit, click the Apply button to save your adjustments. After reviewing the deconvoluted results, you should see the prominent 9+, 10+, and 11+ charge species, which I have annotated here. Note the monoisotopic mass for these species in the mass list. When you are finished, do not forget to save your results under the File function located on the top left corner. Next, we will use MSMS data file for fragment matching. In the same manner, use the Import Data function in the Discovery Mode node to import the sample bruker.d native ECD folder. You should now see the raw data in the top center panel. To complete the database search, Users must label the spectrum as MS2 data. To do this, click the chromatogram button in the center panel. Then double-click where it says MS, and in the pop-up window, change the MS level to 2 and press OK. Once this is complete, click Process Data in the Discovery Mode node to open the Process Wizard dialog. The Process Wizard will set up the series of tasks for selecting, configuring, and running the deconvolution and database search algorithms. Here, select the eThrash deconvolution algorithm. Next, make sure the Do Database Search button is checked, and then select the MS-Align Plus database search algorithm. Once this is done, click on the Browse button to locate the necessary FASTA file for database searching. Select the bovine uniprot FASTA file from your native tutorial folder and load it into MashNative by clicking Open. To set advanced parameters, click on the Advanced tab in the Process Wizard. Here, set the activation method to ETD-ECD. Next, enter the precursor mass to charge 2909.8005. Now we can enter the precursor charge state 10 and then hit the Tab button on your keyboard. You should now see the calculated monoisotopic mass for the protein. Next, we want to enter the deconvolution parameters under the deconvolution tab. Once here, we can enter the deconvolution parameters included in this display. When doing this, it is important to keep in mind the deconvolution results from our MS1 spectra analysis and the calculated monoisotopic mass. Once you have done this, go back to the Basic tab. When in the Basic tab, click on the Start button in the bottom right corner to start the analysis. The status of the analysis can be observed in the Workflow Manager. Once the run is complete, the queued workflow box will be empty. Users will then see that the completed workflow box will be populated. This indicates that your analysis has been finished. After your analysis is finished, you can close the Workflow Manager to view your results. You can review the results of your protein search in the center panel under the Protein Search Results tab. Here you can expand the protein name column. When you do this, we see the protein identified as bovine carbonic anhydrase. Known modifications for this protein can be found at uniprot.org. In the main search box of uniprot.org, you can search for bovine carbonic anhydrase. When we do this, we can see that bovine carbonic anhydrase is the top search. Here we can select on this protein. Given that the observed monoisotopic mass for our MS1 spectral deconvolution differs from the known unmodified sequence mass, we can review the information here for known modifications. Here we observe that the N-terminal methionine is known to be cleaved on this protein. Additionally, we see that the N-terminal serine is known to be acetylated. It is important to note also that this protein is known to bind zinc at positions 94, 96, and 119. With this information, we can modify the protein sequence to reflect our modifications in MashNative. To do this, go to the Tools menu in the MashNative interface. Once there, go to the Configuration selection and then Modifications in the Configuration dialog. Note that one zinc will replace 2 protons when bound to the protein. With this, we can add one modification for a protein loss and also one for the addition of a zinc minus the second proton, as seen here in the 2 bottom rows. Once you have done this, click OK. We can then modify the sequence of our protein to reflect the information we observed in UniProt. To do this, click on the Modify Sequence dialog in the bottom right corner. To make it easy, you can copy and paste the sequence found in the Getting Started guide. Note that this sequence information was taken from UniProt. Once this is complete, click OK. You will now see the sequence is changed in the panel on the right. You can expand this panel to see the entire sequence. Next, add the acetylation to the serine found now in position 1. To do this, click on the S and go to the Custom Modifications. Here, select acetylation. Once modified, the serine will be blue. Similarly, select the histidine at position 93 and remove a proton with your custom modification. From here, we can add the zinc and remove another proton by selecting the histidine in position 95. Here, we can select our custom modification where we subtract a proton and add the zinc. Once we have all of our modifications in our sequence, we can then observe matching fragments. To do this, we need to check the C and Z ions under the fragment ion types. Once we have done this, we can click the Show Assignments button to view our matching fragments. Users can now manually review isotopic peak fit and adjust theoretical fit as needed in the mass list, as we previously discussed in the deconvolution and evaluation of isotopic fit for the native MS1 spectra. Additionally, users can restrict the mass tolerance and use the internal fragment options to improve sequence coverage. Change the mass tolerance to 20 in the error tolerance box. Observe the remaining mass fragment matches once the error tolerance is made more stringent. Finally, note the monoisotopic mass and the number of C and Z ions. When your analysis is complete, do not forget to save your results under the file extension found in the upper left corner. Next, in part 4 of this short tutorial series, I will introduce the use of the targeted mode workflow for characterization of a known protein.